Professor and Dr. Deshinta Arrova Dewi is a distinguished academic researcher and innovator specializing in artificial intelligence and big data analytics. She earned his doctorate from University Kebangsaan, Malaysia, focusing on applying AI to enhance efficiency and innovation across education, economics, and healthcare sectors. Dr. Deshinta has an impressive portfolio of award-winning AI solutions, including predictive machine learning, algorithms, and adaptive learning models that have transformed technology-based education. As an educator, she inspires students through interactive, practice-oriented teaching and frequently serves as a keynote speaker at international AI conferences, sharing insights on leveraging AI to address digital era challenges. A prolific researcher, Dr. Deshinta has published extensively in top journals and leads cross-disciplinary projects aimed at sustainable AI-driven community empowerments. Her contributions and leadership makes her a prominent figure in artificial intelligence and digital technology. Please join me in welcoming our speaker, Dr. Deshinta Arrova Devi.
Thank you, Mr. Kiran, for your introduction. Good day to everyone. So I would like to share my screen. Am I audible and the screen is clear to you?
Yeah, it's visible and you are audible.
Thank you so much. Okay, ladies and gentlemen, for today's presentation, I would like to share about multi-objective routing that usually we use as a solution in the smart cities problem. So the topic that I would like to highlight for today is from the shortest route, and then we are going to move to the master's multi-objective routing. The content for today, I make it like straightforward. So we will look at the rise of the smart city solutions. I originally from Indonesia, and I have been working in Malaysia for 22 years, and we are developing countries, and this is where we are looking at smart cities as the one of the solution that we are facing in the both countries at the moment, and also in the Southeast Asia countries commonly. Then after that, we are going to see the multi-objective route optimization, and I would like to share a case study exploring the alternative metrics in the context of the multi-objective route optimization. Then we are going to see the future directions. Ladies and gentlemen, in 2050, around 68% of the global population will live in the city, and then the traditional cities contribute around 75% of the global CO2 emissions, and the traffic congestion in major city leads to the productivity losses and also increased air pollution. When we talk about a smart city, basically it's an urban area that use technology, data, and innovative solutions. So basically, the aim is to enhance the quality for the residents, optimize the resources management, and improve the overall urban operations. So as urbanization accelerates, basically it includes a lot of things, including the traffic congestion, pollution, inefficiency, and this is where in the optimization using AI, we are looking at a solution using multi-objective route optimization. Basically, it tries to enhance the urban mobility by balancing not only one objective, but it's use multiple objectives. For example, in terms of the travel time, cost, energy efficiency, and also environmental impact. So basically, what are the moral? It is like route optimization is a decision-making process that aims to optimize a set of the objectives simultaneously. So basically, it involves balancing multiple conflicting goals usually. So for example, we would like to, in the smart cities, we would like to minimize our travel time and also minimize the fuel consumption, but also we would like to maximize the comfort and convenience. So how basically we can achieve all those, although it's not like at the maximum rate, but then it is at the compromise percentage, but then we can cover all the multiple objectives in a way. So, talking about AI, we are talking about the algorithm. What are the algorithm that enable us to see or to simulate if we would like to achieve the multi-objective optimization. So there are three, basically there are three famous or classic algorithm. We are talking about NSGA2 algorithm that it is good if we need the diverse set of the trade-off, which is it is best for the finding multiple trade-off solution. But then if we want to have some fast or simple optimization, then we can consider PSO. And then this is for the quick optimization with the fewer calculation. And also, if we need a structure control over complex problem, then we can consider using MOAE, which is it is best for the large scale problems, which is needing the structure search. So PSO is stand for the particle swarm optimization, which is very famous algorithm in AI for optimization. And also we have MOEAD, which is multi-objective evolutionary algorithm based on the decomposition. Now, just one of the algorithm which is very famous is the GA. What are the GA algorithm? Basically, it's an optimization technique inspired by the natural selection. So just say it it try to find the best solution by mimicking evolution, including selection, mutation, crossover, etc. So why GA is very best, because if we would like to see a problem, then we have multiple solutions for that. Then no need for us to visit all the possible solution, so we can just try randomly for the solution. Then after that, we try to find the best solution based on whatever we have at the moment, which is no need to visit all the possible solution. So just say as a demonstration, so just say we are talking about a delivery company that the goal is actually to find the best order to visit the cities, which is they consider the shortest distance. So just say the cities to visit, it is started from A, then after that it moves to B, city B, C, D, E, then after that it comes back to the A. So how basically GA algorithm will find the solution for this problem? So the first one, the technique basically is to create possible solution, or in GA it is famous as a population. So this is where we can initiate initial route, and then this route, every possible route is considered as the chromosome. So just say we just generate 4 chromosomes based on the cities that we need to visit, and this is the 4 chromosome that has been generated. So from there, we are going to do the next step, which is finding the fitness score for each route. So for each chromosome, we are going to calculate the best performance, and we can see that because our aim basically to find the shortest distance, then we can see the shortest distance will be the first solution, which is 150 kilometers. So this is the best chromosome that we have. But the GA does not stop until there. So we try to explore choosing the best parents. So we know the best parents will be the first solution. Then we want to find the second best solution. And we want to explore, is there any other possible ways which is a shorter distance compared with the solution that we have. So what we are going to do over here based on the GA methodology is to find the best and second best. Then from there, we are going to implement the steps in the GA, which is a crossover, to generate the new offspring after the step, which is the crossover. So the crossover solution basically it will produce from the parent A and parent B. So we have the child 1, which is the combination of the ACB with the next parent 2. So we have ACBBA, and which is consider, we will do some validation based on the AI generation, and we can do through the validation that we can see that the first child basically is invalid because the city of B appears twice. And this is where we can move to another solution, which is considering the parent 2 and then combined with the parent 1. So this is ACDBA, and this is considered as valid as the new possible route. We want to compare whether the new possible route having a better performance compared with the initial population. Then the next step in the GA is basically a mutation. So different with the crossover, whereby it involved two chromosomes. For the mutation, it involved only one chromosome. So we can see that the comparison before mutation. So for example, we choose ACDBA as the root. Then after that, after mutation, we swap between C and D, and then we are going to calculate the performance. And then we can see that the performance is to find the final best root. Which is found compared with the one that we have just now. So upon 150 kilometer from this GA generation of root, then we can find the shortest distance 140 kilometer, which is not appear in the first population that we have. So this is how GA works, and then it considered the best because it finds solution without checking all possible routes, and then it can learn and improve over multiple generation. Ladies and gentlemen, nowadays in AI, machine learning approaches are very famous. So just looking at another possibility whether it is possible to find the best route using machine learning approaches. So this is why I would like to share. We have also many algorithms. And for example, over here we have 5 algorithms. One of them is using reinforcement learning. So another algorithm basically, is multi-objective, evolutionary, multitask learning, Bayesian optimization, and then transfer learning specifically for Moro. But we just want to see how reinforcement learning compared to the GA just now. Reinforcement learning basically is a machine learning based algorithm, but this one is using DQ learning. It is based on trial and error method where the AI agent learns by exploring and remembering what works best. So for example, as the what we call as a simulation. So we use the Q tables and then stores the Q table. Basically, it will store the best action for each state. And then the agent is like a robot. Yeah. Then after that, the Q table is like a map that help the agent remember the best way to reach the goal. Then after that, it has the learning process whereby the agent exploring different paths and remembering which one is the best. So as a simulation, just say we have the one environment or grid. We have 5 times 5 grid. Agent start with 0.0 over here as the coordinate. Then the goal will be 4.4 over here. Then the agent can move basically up, down, left, right, and so on. And each step will give a penalty -1. So the agent because have not reached the goal yet. And then if the agent reach the goal, then it will get the rewards. For example, we can put the reward as +10. So it works with the Q table. So how the Q tables work, basically it comprises of the rows and column. Then after that, the agent can start from the state 0.0. Then after that, it can goes up, down, left, right, and then it will see the highest values. For example, over here, the highest value will be 10 for the right, so it always move right. So if it's in the 1.0, then it will move right again because it is considered is the highest value inside the Q tables. So in finding the shortest path compared with the GA algorithm just now, so the Q table will get updated all the time and it has some formula applies. So for example, over here we have some grid representation, and it starts S will be the starting point, and then the G over here will be the goal point. And this is where the steps taken by the agent. I just record over here, so it requires like 8 steps. So it starts from the 0.0, it moves right. So when it moves right, then it will move to the 0.1. Then after it will move right again, then it will go to the 0.2 and so on. So basically, the agent will learn that it will find the shortest path in the 8 move. So now every time the agent starts from 0.0 based on the learning process that it has done. So the agent will follow the exact route to reach 4.4 as fast as possible. So beside the PPO and deep Q learning, so we have another algorithm which is policy-based method compared with the deep Q learning. So I will just skip this part because we are focusing on the what we call the GA. Yeah, this one just for overview for the optimization. Now, let us see the exploring alternative metrics with the Moro. So just say we have a logistic company who would like to optimize its delivery route to reduce delivery time, and then it would like to minimum the fuel consumption and also the lower carbon emission. So the company operates 100 delivery truck daily, serving 500 customer location across the city. So basically, traditional simple single objective route planning focus only the shortest distance only, or fastest travel time, or minimizing emission only. But then for the Moro, it will try to find solution where we want to achieve all these objectives, minimizing the delivery time, minimizing the fuel consumption, and also minimizing the emission. So what are the step-by-step solution approach brought by the Moro algorithm? So the first one, consider as the data collection. So can be varieties of data, can be the traffic data, weather data, fuel consumption model, the emission model, and also the delivery constraints. So this is where the traffic data can be from the road congestion, the weather data can be the rain or extreme condition that may affect the route choices. And then we have fuel consumption model. So this one basically vehicle type, load, driving condition, and so on. And we have also emission model estimated based on vehicle speed and also engine efficiency. For delivery constraint can be delivery time windows, whereby the customer would like to have some choices at what time they wish to receive their parcels. And also we talk about vehicle capacity and also the road restriction. So basically in the data collection, it is possible to collect all the data, then it will be we use the AI agent to find the optimal solution. So the second step in the Moro, we define the optimization problem. So in this view, we create a function to minimize the travel time, the function to minimize the fuel consumption, and also the function to minimize the carbon emission. Then after that, we can apply to any algorithm. For example, over here, we use multi-objective optimization algorithm, which is NSGA2, the one that I've demonstrated earlier. So in the NSGA2 algorithm, this is the step basically. You can see here. So I just make it short. So basically, NSGA2 algorithm will find the best trade-off between the multiple objective goals that we like to achieve. So how does NSGA2 works in this case? So basically, it will similar with the GA algorithm. A genetic algorithm. The first one, it will create the initial population. It will start with the randomly generated roots. Then after that, each root represented as a chromosome. Then after that, it will evaluate the fitness of each root, which is considered to calculate the travel time, the fuel consumption, and also emission. Then after that, we have non-dominated sorting. So this is where the rank solution, it is based on Pareto dominance, which is no single solution is the best for all objective, meaning that we consider all the three objective. Then after that, they will use the crossover mutation to generate the new roots combining the part of the base solution. Then after that, introduce small mutation, random root changes. Then after that, we will select the best Pareto front solution. So just to give you overview about the Python codes for that. So here we set the random seed for the reproducibility. Then after that, we define the multiple objective optimization problems. So this is the fitness function and also individual. We define the constants for the problem. Then after that, we generate, this is the data. It's just synthetic data. So this is like travel time, fuel consumption, emission data, and so on. Then after that, we can initial population. So we use the toolbox population, for example, for 100 data. Then after that, we have number of generation. We have population size that we can change if we want to see another part of data. Then after that, we have a lambda for the offspring size. Then after that, we have also crossover probability. We set up here as 0.7 and also mutation probability as 0.2. So once we're running the algorithm, basically, this is where Pareto front will give a suggestion. Since we have multiple objects objective route optimization. So this is the solution which is suggested by the Pareto Front. So we can select on this one. This is most probably the best solution, whereby we can minimize the travel time, minimize the fuel consumption, and also minimize the CO emission. Or else we can see another solution. Perhaps we cannot really minimize the travel time and also the fuel consumption, but then we can reduce on the CO2 emission. So basically the Pareto front that we are looking at over here is the key idea is the no solution, which is strictly better than another. So we can improve one objective, but somehow we have to compromise another objective. So the solution represent the trade-off between the travel time, fuel consumption, and emission can be considered three. Solution A can be fastest delivery, but then higher fuel consumption, or can be most fuel efficient, but then longer delivery time, or can be the balance time, cost, and emission. So the final decision making based on the simulation that we have, for example, we choose for solution C, which is a balance between the time, cost, and also emission. So this is where we are able to reduce delivery time, perhaps not that much, but then it is only 20% compared to the previous method. Then we can cut the fuel cost, perhaps cannot be like 20% or more percentage, but then we can cut the fuel cost by 15% due to the optimized route. And another one can be the lower carbon emission by 18%, for example, which is contribute to the sustainability goals or a green work that mostly people are looking at now. So what are the future directions from here? So can be AI driven real time, the route optimization, can be integrated smart transportation data, can be IoT, big data, and also AI, can be sustainability and green routing for the eco-friendly cities. It can be the future for the smart city, can be IoT, big data, or sustainability, green computing for the CO2 reduction, and so on. So basically, that's my presentation for today, and thank you for listening. Back to you, Mr. Kiran. Thank you.